Hello, Dan. So we usually start right at 11, so I'll wait to have you do your announcement then.
Be okay if I share my screen when it's 11?
Mhm. Yeah, Dan, if you actually want to wait until about 11:01, just in case if we have a few late people.
Just let me know when.
Okay, sounds good. All right, so I think you should be able to share your screen. I think I have that as an option for you. Okay, very cool. Hi, everyone. This is Dan. He works at the Math Learning Center, and he's here to talk about them. I'll see you a little bit.
Awesome. Thank you, Patrick. So, hi, everyone. I'm Dan from the Math Learning Center, and we are currently accepting more coaches to work starting in the fall semester. So, what is the Math Learning Center? Many of you may have been to the Math Learning Center, many may have not. So, what the Math Learning Center is, it's where students help students with math classes. And the math classes that we mostly help with are Calculus 1 through differential equations. And the minimum requirements to start off as a coach is just having like the Calc 1 and Calc 2 knowledge. But then by spring of next year, if you had completed linear algebra and differential equations, that'd be great. And then statistics is a plus but not required. So I bet most of you in this class already have most of these requirements filled out and you're working on linear algebra. So that's really great. It's a really fun job to be a coach. So you get to meet a lot of other people. So you can see we have a picture here. When we hire people, so you'd start in the fall again, and we don't feel like you ever would be stuck. Like we make sure to train you. So we have weekly meetings for the first semester, an hour meeting, which counts as work, and we would make sure to train you, give you all the resources that you would need, any questions that you have about being a coach. So like even if you're like on the fence about whether or not you can be a coach, definitely try, because there still is like the training process too. And how do you apply? Well, you can see one of these posters on campus, follow the link there. But the link you can also find at MTU MLC. I'll put it in the chat before I leave. But the first link on our homepage here, so on the Math Learning Center homepage, it has all the things that you need to do to apply. Like we just have a few questions that we need to fill out and whatnot. So the deadline for the application, you have some time to kind of mold over. It's due around week 5. Specifically, it's due February 10th and 11th. So that'll be the deadline for our application. And again, you can email it to us, but that's all filled out in the application. So as a coach, the minimum hours is around 7 hours per week, 7 hours that you're available. You may not work those full 7 hours, or you may work more. Either way works. And it is a paid job. So I know that's always the question. And I really love my job. I've been there for 3 years now. I started off as a regular coach, and there's room for growth. So you could get promoted to an executive coach if you wanted, if that's like something that's important to you. So there's definitely room for growth for sure. And you get to meet a lot of new people, which is really nice. Students and coworkers. Do you guys have any questions? And thank you all for listening. Awesome. Okay.
Thank you, Dan.
A lot of you later applying. It'd be really great to have you on the team. I'll put the link in chat really quick.
Okay. Yeah, thank you very much, Dan. I was also a Math Learning Center coach when I was younger, and that was my favorite campus job I've had, and it was very nice. So, well, thank you very much, Dan. Have a good day.
You too. Thank you.
Thanks for stopping by. All right. And if any of you guys want to ask me questions about the MLC, you can at the end of class, and I'll stick around too, or with any homework questions you have. All right, I'll do a quick announcements. So today is Wednesday. We're going over section 1.4. And so you'll have homeworks 1.3 and 1.4 due Saturday at midnight. So those 2 homeworks are due at midnight. And remember, I have office hours today at 1 and also office hours tomorrow at 1 o'clock also. If those don't work for you, just email me and we'll set up a time. All right. And I'm gonna stop my video and share my screen and jump right into 1.4. All right, learning objectives for 1.4. In case anyone can't see red and green at the same time. All right, we're going to deal with the matrix equation. So we'll define the matrix equation. AX equals B. All right, I'm going to make sure everyone's on mute. There we go. And then we're going to relate this matrix equation to everything that we've learned so far. So that's the main objective for today. We're going to define the matrix equation, and that's going to be called AX equals B, and we'll relate it to the previous sections that we've gone over so far. All right, and I have a question right away for you. This is relating to last class when we talked about span. And I'll write it on the slide if you want to take a moment and think about it, make it a little bit more clear. Can the two vectors, 1, 1, and -1, -1, if we take the span of that, would that equal R2? So can that span, say, the whole XY plane, just using those two vectors? And I have two other poll questions later, one in the middle and kind of one at the end. So this is the first one. So if we take these two vectors and find all the linear combinations, remember that's what span means, take all the linear combinations of these two vectors, will we span R2? And that is, can we span the whole XY plane? All right, give you 5 seconds. 4, 3, 2, 1. All right, I'm not going to share the results because actually the majority of you didn't quite get it. So I'm going to ask one more time, but before I ask, I'm going to draw a little graph here. So if we have our XY plane, and we have the vector 1, 1, and then the vector -1, -1. Using those two vectors, can we span the whole XY plane? And remember, span means if we take all the linear combinations of these two vectors, can we get any point in R2 or any point in the XY plane? I'm going to ask one more time and see if we can do a little better after seeing that plot. So, okay, let's try again. Using those two vectors that I plotted, 1, 1, and -1, -1, can you get any point you want in the XY plane? I'll give you another 10 seconds. 3, 2, 1. Okay, very nice. So you guys kind of flip sides to say with these two vectors, you cannot span R2. So very nice. The only thing these two vectors can span, since they're actually scalar multiples of each other, they can only span a line. They can't span the whole plane. So if I drew a little line here, these two vectors can give you any vector on this line, but it can't give you something, say, over here. You'd never be able to get that point using those two vectors with linear combinations of those. So the only time you can get all of R2 is if those two vectors do not lie on the same line. Okay, so that's a little review from yesterday. Okay. Oh, and I didn't share the results there. So there you go. The answer is no. Most of you got it that time. Okay. Okay, let's move on to the new content. So, oops, let me erase this. Forgot to erase that. And did someone have a question? I heard, okay, just gonna mute you. Okay, there we go. So here's the definition that you should write down. And this is the big definition for today. This is defining what A times X is, a matrix times a vector. So if A is an m by n matrix, remember it's rows by columns, so m times n by n, with columns A1 through AN, so it's n columns. And if X is an Rn, that means it has n elements or n entries, right? So R to the n is all the vectors that have n entries. So R2 means all the vectors all the vectors that have 2 entries. That builds Rn. The product of A and X, denoted by AX, is the linear combination of the columns of A using corresponding entries in X as weights. So this right here, these are columns. So it's kind of in this compact notation right now, but recognize this whole thing is a matrix with n columns. And this is our vector X. And we're defining that to be this, the linear combination of the columns of our matrix using our entries in our X vector as weights. And I'm going to show you quite a few examples so we can understand what this definition is. So if we have this matrix, let's say 5, -2, 1, 7. I just made those numbers up. This is our matrix A, and it has 2 columns. So this right here, that's A1, and that column right there, that's A2. So that's the meaning of these. Those are columns of A. All right, I'm gonna erase that just so it doesn't look as messy. And then if we multiply it by a vector X, a column vector in particular, we're only gonna be dealing with column vectors here. So we multiply it by that vector, and this is X here. What that is, and this is what we're gonna write down on this right side, that's equal to X1 times the first column, 5, 1, plus X2 times the second column, -2, 7. So we did this right here, X1 times A1. So this is A1 right here, and this is A2. And the main way to remember this is the first entry in the vector X goes in front of the first column of matrix A. The second entry in the vector X, so X2, goes in front of the second column of matrix A, so A2. And that's the big idea for today. So we're going to do a lot of examples and solve some problems with this new notation. So really this is new notation, and we'll relate it to older stuff we've done. And this new notation is going to be very helpful in the future to think about it as a matrix and a vector multiplication. Okay, so I'll show you another example. Let's do a 3 by 3. Let's do 1, 2, 3, 4, 5, 6, 7, 8, 9. And let's make up some numbers for X1, X2. Let's do -4, 9, and 3. So what is that equal to? Well, I take the first entry in our vector X. So this is X and this is A. Take the first entry in X and multiply it by the first column. And then we take the second entry in X, and that's a 9, and multiply it by the second column in A. And we take the third entry, which is 3, and multiply it by the third column. All right. And you could add those vectors together like we were doing it on Monday, where you add vectors together and you get a resulting vector out of that. I could do that right now. And so this would be -4, -16, -28, plus 18, 45, 72, plus 9, 18, 27. Okay, I don't want to do all that mental math, but you could figure out the resulting vector by adding the corresponding components of each vector. So -4 plus 18 plus 9 would give you the first entry in the resulting vector, and so on. Okay, any questions with those two examples? Anything in the chat? Or anyone want to unmute themselves? So this is the main definition for today, and we're going to be using this a lot throughout the rest of this semester. Okay, let's do some more examples. So I have another poll question for you, second one for today already. Is this possible? So take a moment, see if you can write this down as a linear combination of the columns of A. Oops, sorry. There we go. So does this make any sense? Yes or no? So look at the definition that we just looked at. Can you write down the linear combination? Okay, 5 more seconds. 4, 3, 2, 1. All right. So most of you said no. Let's check it out. All right. So if I'm going to write this out, then I would have the first entry in X times the first column plus the second entry times the second column plus, and now there is no third entry in X, and we still need to multiply by the third column. So this does not make any sense. So very nice. Most of you said no. You need to have the same number of entries in X as there are columns. There's only 2 entries in X, but there's 3 columns in A. So that doesn't make any sense according to our definition. So let's just go back to our definition. Our last thing that we're adding is going to be xn an. So therefore, there need to be the same number of elements in X, that is n elements or n entries, as there are columns of A. There needs to be n columns. So you have to have the same number of entries in X as there are columns of A. So that doesn't make any sense. Let's look at another one. So my right makes no sense, not possible. All right, let's look at another one. If we did 1, 2, 3, 4, and x1, x2, x3. Well, let me actually put numbers in here. Let's do 5, 6, 7. Does that make any sense? Well, no, it doesn't. Not possible. Because there are 3 entries in our vector X and only 2 columns in A. So according to our definition, we just can't do this. You can't have that matrix being multiplied by that vector. Now let's look at another one where it looks a little bit different than the one that was possible in our previous slide. Let's do 1, 7, 4, 2, 8, 3. Multiply that by the vector -10, 11, 14. Well, is this possible? Well, yes, it is, because there's 3 entries in our vector X and 3 columns in our matrix A. So this is A and this is X. So this works out, and this would be our first entry in X times our vector 1, 2. That's our first column in A. So that's A1. This is X1. Plus 11 times 7, 8. Plus 14, 4, 3. Okay. And you could figure out what this is equal to. There'd be one vector that has 2 entries if you added those up. But the main point here is this was possible because there were 3 columns and also 3 entries in X. So according to our definition, we can have this matrix being multiplied by this column vector. X2, A2, X3, A3. Okay, so hopefully that's enough examples to demonstrate the meaning of a matrix times a vector. Sometimes, another way people think about this is if you take this vector here and kind of rotate it on top, then you have negative 10, 11, 14. And you kind of separate these. You're multiplying negative 10 by the vector 1, 2, 11 by 7, 8, 14 by 4, 3. So a way to check the size is if you rotate this vector, negative 10, 11, 14, rotate it on top. Oh, now the size match is 3 wide for the vector x and for the matrix A, if you rotate it. So that's a way to think about it too. Okay, any questions with the definition of a matrix times a vector? So you can't take any matrix and multiply by any vector. The vector has to have the same number of entries as there are columns of A. All right, we're gonna move on. So check out this matrix, AX equals B. So matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are the entries of our matrix. We're multiplying it by a vector, x1, x2, x3. Those could be numbers. Right now, we're just going to call it x1, x2, and x3. And we want to set it equal to this vector b. Okay, so we just talked about, we can rewrite this matrix times a vector as, so we can rewrite this as a linear combination of the columns of A. Right? Take the first entry, multiply by the first column, add it to the second entry times the second column, and so on. And now it looks like what we're doing on Monday. So this is a linear combination of vectors, and we're trying to see if it will equal this vector b, negative 2, 4, negative 12. So these two are equivalent. These are saying the same thing with the new definition that we learned today. But on Monday, we talked about, oh, we can take a number and multiply it by a vector. So this x1 can be multiplied by the 1, 4, and 7. And so we get these right here. We can multiply the x2 and multiply it by the vector 2, 5, 8. And we get that. And then so on. And we end up getting a system of equations because we want the first entry in all the vectors to add up to negative 2. We end up getting a system of equations. So these two are equivalent also. And that means these two are equivalent since these two are equivalent. So they're all equivalent to each other. And really what they are is there's different ways, different kind of notations, different language of describing the same exact thing. So think about if I'm asking you if you're hungry right now, I could say hungry, question mark. I could say food, question mark. I could say lunch, question mark. So there's 3 different ways of expressing the same meaning. And that's exactly what we have here. And what this is called, the top one, this is called the matrix equation. What we learned on Monday, this is the vector equation. And what we learned week 1, this is the system of equations. They're all equivalent, just kind of a different language. And they're all helpful to think about it in one particular way or another. So sometimes it's helpful to think about it as system equations. Sometimes it's helpful to think of it as a vector equation, because then we can start talking about span and linear combinations and things like that. So it has its own kind of perspective on the question. Then we also have the matrix equation, and that will give you a new perspective kind of later on in the course. Right now, we're just going to think of it mostly as a vector equation written in a different way. But we'll see how the matrix equation can be helpful later on. And this is the big AX equals B. So if you were to characterize this class, you could tell someone you're solving AX equals B with a matrix and a vector. Now there's a lot more to it, and we obviously still have like 10 more weeks left, but sometime in essence, the class can be reduced to ax equals b, and you're solving that equation. But that one equation can solve many types of different scenarios. We're going to learn about those later on. Okay, any question about these being equivalent to each other? So the left two, the matrix equation, vector equation is equivalent from the definition from today. And then we learned on Monday, the vector equation is saying the same thing as a system of equations. Now there's one method to solve all of these. So this is algebra, right? Algebra means we're solving for the unknown x. So we want to solve for this x here. We want to solve for the x1, x2, x3 in the vector equation. Or we want to solve these here, right? These are all linear, and algebra means we're solving for the unknown, and it's x in this case. So how do we do this? For all of them, what we do is we augment the matrix. So we have 1, 4, 7, 2, 5, 8, 3, 6, 9. Augment the matrix with -2, 4, -12. And we're going to REF that. Remember, reduced echelon form. We're going to turn that into reduced echelon form, and we'll answer the question of what is x. We're going to solve for the unknown. So the one method of REFing will answer all these three questions for the matrix equation, vector equation, and system of equations, because those questions are all equivalent to each other. Okay, any questions before I move on to the next slide? I'm going to go into a theorem in a minute. Okay, I'm not seeing any questions. So if you have a question later, I can always run back to this slide. Okay, theorem 4, it's number 4 in the book, so I left it called theorem 4. And we're letting A be an m by n matrix, so it has m rows and n columns. And the following statements are logically equivalent. That is, for a particular A, either they are all true statements or they are all false. So let's just talk about that first before looking at A, B, C, D. Logically equivalent means if any of these statements are true, say you figured out A is true, well then that means B, C, and D are also true because they're logically equivalent. If you find out any one of these is false, if say D is false, then without checking A, B, and C, you can say right away A, B, and C is also false because they're logically equivalent. So that's what logically equivalent means. That means they all stand together, they all fall together. That's logical equivalence. So pretty cool. Okay, so let's start with B right here. And instead of being super general and abstract, let's let M be 2, so we're talking about R2. So let's talk about R2, because it's easy to visualize it as XY plane. Okay, so each B in R2 is a linear combination of the columns of A. So let me write down some matrix A. Let's do 1, 2, and 0, 1. So let's let that be A. And then we're going to have our X vector. And we're going to have some unknown B. Let's call it B1, B2. And part B is saying every vector B in R2, so that means any vector in the XY plane, we're going to say that's a linear combination of the columns of A. Okay, is that true for this matrix? So let's make a little plot. And our columns are, let's see, 1, 0. So let me do a different color. So 1, 0 says right here. And then 2, 1, that would be like right here. Okay, so we talked about before, as long as these two vectors don't lie in the same line, they can produce all of R2. You can get some linear combination to produce any point in the XY plane. So this is true that this matrix, let's see, the columns of A, any linear combination of those can produce any vector B in R2. So that's what this is saying for part B. So give me any vector B, say it's over here. I can give you B as a linear combination of my columns of A because my columns of A don't lie on the same line. They have an angle that's not 0 or 180 degrees between them. That's what part B is saying. Okay, so B is true. And also for each B in R2, the equation AX equals B has a solution. And that's not too hard to see based on what we have written here, because if we augment the matrix 1, 2, 0, 1, B1, B2, this is kind of what we did the first week. This will always have a solution. The only time it wouldn't have a solution if this number was actually a 0 instead, then we'd have a contradiction because it'd be saying 0 times x2 equals b2. And if b2 was not 0, then it'd be saying 0 times x2 equals, say, 3. And that's impossible. But because that's not a 0 right there, we actually have a pivot position. And that's relating to part D. We do have a pivot position in each row of A, if we're just looking at this right here as our A. That has a pivot in position in each row. So therefore, AX equals B has a solution. So the only time we don't have a solution is if this entry right here was actually a 0. So if B is true, then A and D are also true. And C is a little bit trickier to think about. But going back to our plot here, since our columns of A can span R of M, now if we choose any B, that will always be in our span. Our two vectors span R2. That means it gives us the whole XY plane. And so any B I choose in the XY plane, I can produce that with my two column vectors. That gives us part C. Now let's think about it the other way real quick. If the columns of A did not span R2, so that was false, part C was false, and say my two vectors were on the same line like that, I could not produce this B. So AX equals B has no solution. The columns of A do not span R2. B is not a linear combination of the columns of A. And we wouldn't have a pivot position in each row for our matrix A. And so those are all falling together. So they all stand together or they all fall together. So this theorem is a lot more helpful if you visualize it in R2, and then you can extend it to any RM after that. Okay. This theorem is saying equivalent statements, just like how our last slide is having different equivalent descriptions of the same thing. That's pretty much what theorem 4 is also doing. Okay, so I'm going to move on to your homework. So we got about 15 minutes left. I think we need some examples to learn this section better. So these questions are based off or straight from your homework. And before we get in, let's just take a little mental break. And I have a little math joke for you. It's the only math joke I know. So what's the volume of a pizza? If the radius equals Z, and then the thickness equals A. So if anybody knows the answer to the joke, you can put in the chat. Oh man, very nice, Hunter. You already figured it out. The answer is pizza because it's pi times r squared for the area of a circle times the thickness. That's pi times the radius is Z. So Z squared times the thickness, or Z squared is also Z times Z. Very nice. Okay, good little mental break. Okay, first homework question, use the definition of AX to write the matrix equation as a vector equation. So when you see the word definition, if you didn't take notes or you didn't print off my notes that I put on Canvas after, you can always go to the ebook, and the ebook would have this definition right here. So if you see definition, that means the definition came from the book. And they want you to write this out right here. So that's the definition that we've learned today. That x1 times the first column plus x2 times the next column. So this is x1 and x2. So what do we got to do? We got to write x1 times the first column plus x2 times the second column of matrix A. And that's equal to negative 20, 49, 20, 20. Okay, so that's what they want you to put here. I heard on the last homework, some people were having trouble typing vectors in. If that was you, maybe if you could stick around after class and maybe show me what's happening with the shared screen. I'd kind of like to see what's happening too, because I wasn't having the problem on my computer, so I wonder if there's some other issue. Okay, so this problem was writing the matrix equation as a vector equation based on the definition that we learned today. Any questions on that one? Okay. Again, this is matrix A, this is vector X, and we like to call this vector B. All right, I have a question for you here. So last poll question for today. What number goes in the red circle? I'll give you about 10 more seconds. What number will go in the circle? So we're trying to write this vector equation into a matrix equation based on our definition. 5, 4, 3. Looks like a few of you still have to vote. All right. Okay, very nice. We got to put a 7 there. So let's put the 7 there. Oops. 7. And how do we fill in the rest? Well, this is the first column of our matrix. So 2, negative 4, 6. Negative 3 is our second column. Third column. Very nice. We're multiplying that by the vector x1, x2, x3. So this is the vector x. Okay, very nice. Next question, use the definition of AX to write the vector equation as a matrix equation. It's the same thing again. This time they gave you Z1, Z2, Z3, Z4 instead of X1, X2, X3, X4. So these will correspond to the matrix columns, A1, A2, A3, A4. Then we have a vector Z. So we really have A times Z is equal to 0, 10. And I'll let you guys figure that one on your own, but I'll give you a hint. The matrix A is going to be a 2 by 4, a 2 by 4 matrix. Okay, so that was one of the questions on your homework. Write the system first as a vector equation and then as a matrix equation. So a little bit of a heads up when you're first answering the first question, where you're written as a vector equation. Oops. When you're doing this part, They kind of gave you some nonsense in the instructions, so this doesn't really make any sense, particularly this first row. Just ignore that. First row is for the next question when they're talking about the matrix equation. So row isn't as meaningful for a vector equation. Okay, so let's see. Write the system as a vector equation. We have the system of equations. So this right here is system of equations. That's the language we're using to describe this problem. But now we want to turn it into the language of a vector equation. So we have our weight x1 being multiplied by the vector 4, 0. And that's because we could put a 0 right here and multiply it by the x1 like that. Then we have our next weight, x2, being multiplied by the vector 1 times 8. And then we next have the next weight, x3, being multiplied by our vector -3, 7. That's equal to 6, 0 vector. So again, this is what we talked about Monday. We can go back and forth between a vector equation and system of equations. So solving for x1, x2, x3 in this problem is equivalent to thinking about, let's see if 6, 0 is a linear combination of these three vectors. So we're kind of approaching it from a different direction, but it's still equivalent. Then later on, they ask you next to get the matrix equation. And so now these are the corresponding columns of matrix A. So A1, A2, and column A3. And you're multiplying it by the vector x. So you have AX equals to 6, 0. And x will be x1, x2, x3. And I'll let you figure out what the matrix A is. All right, let's see. Is there any questions on this? Is everybody, seems like everyone's maybe getting it. Am I getting any questions? Okay, we still have 6 more minutes. I think we have a few more homework questions we can look at. But I'll take a few seconds, see if anyone has questions. Okay. So given A and B to the right, write the augmented matrix for the linear system that corresponds to the matrix equation AX equals B. Then solve the system and write the solution as a vector. Okay, so first I want you to select the correct choice. So what's the size of our augmented matrix? Well, since we're augmenting the matrix, it's not just going to be a 3 by 3 matrix because we're going to augment vector B onto the matrix. So it's really got to be a 3 by 4 matrix. So this is a 3 by 4. That's because we're going to put vector B on the rightmost column like this. Then you're going to re-put matrix A in here. And then how do you solve the system? So then solve the system, write the solution as a vector. So like we talked about on that one slide where all these different descriptions are the same, there's one method to solve all those different descriptions, and that's by doing the REF of the matrix. Convert the matrix into reduced echelon form. So I'll let you do that. We're not going to do that here, but for part B, oops, you want to REF that guy, that augmented matrix. And I'm just going to make up the solution. This is not the actual solution because I'm just guessing numbers. So made up solution. So say you REF it. That means you got 1s on the diagonal and 0s above and below the pivots. And you'll have some numbers here. say -3, 5, 24. So say you've gone from there to there. I'm just gonna make a double note. I just made this up. So no one copies it when they look at the notes later. So say you got to that point where you REF'd it. They want you to write it as a vector. Well, this is saying x1 equals -3, or x1 plus 0x2 plus 0x3 equals -3. So x1 equals -3, x2 equals 5, and x3 equals 24. How do you write that as a vector? Well, x is equal to x1, x2, x3. So that's equal to -3, 5, 24. So that's how you write the solution as a vector. Okay, so we got 2 more minutes, and that was all I have. So we're ending early today. Stick around if you have any questions for me, either about the homework or if about the MLC. If you're interested in maybe coaching there, I can answer any questions you have. But have a good day. I'll see you Monday. And I'm going to stop recording here.